So now that we've found this best line, remember what we want to do is in some sense discard the data. And we can do that by using it for predictions, but there's actually some more that I can dive into. The numbers that are involved, the slope and the intercept, actually might be able to be interpreted, and I can learn something from these numbers. So here's that best line. Let's start with the slope. Okay. Here's the interesting thing about the slope is if I go 1 unit in x, all right, I go up exactly the units in y that are the slope. So this is all relates to the famous saying rise over slope is rise over run. So a run of 1 is equal to a rise of the slope, and I don't want to get into that too much, but that's the that's the true of every place. So notice those two triangles are exactly the same as is the same as this triangle. So every time I go up one shoe size from 6 to 7 or 8 to 9 or 9 to 10 or 10 to 11, I go up in height a certain number of inches, and that height that I go up those inches is 1.962. Okay, so what I can do is summarize this, that for each additional shoe size, we predict the height to go up 1.962 inches. So if I, you know, find out that, my son has grown one shoe size, I can take a guess. His growth is different than adult heights, but I could take a guess that he's probably grown 2 inches in that time, near 2 inches, right? 1.962 inches to be exact, more exact. And so this is always true with any regression. We can say for each increase of 1 unit in the x variable, whatever it happens to be, we predict that y will increase by b1 units. And if b1, by the way, is negative, we mean decrease, of course. Okay. So here's a maybe a better example, I think, than the shoe size. And there's some data from our book that deal with roller coasters, and this data, one part of the data is how tall the initial drop is for these different roller coasters around the U.S., and then what their top speed is in miles per hour. And you can see there's a positive association, and it's linear, and it's pretty strong. There may be a few outliers we have to worry about, but they're not too bad. They won't have too much influence. Why? What could I do with a regression in this case? And the answer is actually, here's the interesting thing. Let's find the line of best fit, and we find that this predicted top speed is equal to 38.5 plus 0.183 times the drop in feet. So let's focus in on that 1.183. How can I interpret that slope? And the answer is, well, every additional foot, every increase in 1 unit in the x direction, okay, and that would be in feet, right? So for every additional foot in height, we would predict the top speed of the roller coaster to increase by 0.183 miles per hour. And that's a really interesting number because it allows, maybe a roller coaster designer to sort of think things through. Well, if we go and build a roller coaster 10 feet higher, right, because we want to, how much kick will we get out of that increase in height? How much faster will the roller coaster go? Okay, and you and I wouldn't have had any idea. Oh yeah, that would increase it by, I don't know, 50 miles per hour. I don't know, 10 feet height. That probably not 50 miles per hour, but I wouldn't be able to make an educated guess. Yet here we have taken actual data from actual roller coasters, and discovered the pattern that indeed, 10 feet higher would increase it by 1.83 miles per hour. Okay. Because why? Well, because each 1 foot increases it by 0.183, and so 10 feet would be 10 times 0.183, which is 1.83 miles per hour. Okay, so I now have a notion of how roller coasters work that I wouldn't have had before. And real roller coasters, you might go ask an engineer or something, and they might be able to do some theoretical calculations. But the beauty of this is that it's based on actual data from actual roller coasters. There's no question that in some sense is closer to the truth than the theory that an engineer might work out. Here's another example for cars. And what this is about, I think it's about 45 cars, where different car models. And what we've done is we've got on the x-axis the weight in thousands of pounds, and that's going to be important in a second, so keep that in mind. And the fuel economy of the cars in miles per gallon. And lo and behold, we see a negative association. Linear is the form, pretty good, and it's pretty strong. Maybe we should say moderate, but the linear form is what we're after. So we can actually find the line of best fit. So we can say the miles per gallon, the estimated, remember the hat, estimated miles per gallon, is 37.285 plus negative 5.344 times the weight. And by the way, it makes sense that this is a negative association because the heavier the car, right? This is 1,000, 2,000, 3,000 pounds. The heavier the car, the less fuel economy, the poorer your fuel economy is going to be. Great. So there's my best fit. And by the way, I'm sorry, I just jumped the gun there a little bit, because what I wanted to make a point is that since this has a negative association, it's going to have a negative correlation. And it turns out, remember, because the slope is just a product of the correlation times the standard deviations, and standard deviations are always positive, that the slope and the correlation will always have the same sign. So a negative slope, a negative correlation, and a negative association are all really the same thing. Okay, but getting back to the example, that the slope on this line is negative 5.344, means that for every unit increase in the x, I get a this much decrease, because it's negative, in the fuel economy in the y. And by the way, 1 unit here going from 2 to 3 means what? It means 1,000 pounds more. So really, what I should be saying is 1 unit, but 1 unit in the x is really 1,000 pounds. So for each 1,000 pounds of weight I add to the car, we're going to predict that the fuel economy will decrease by 5.344 miles per gallon. And again, this is something that engineers who make cars would really love to know, because they have all these design decisions they have to balance and take care of. And so, adding weight, how much is that going to hurt our fuel economy? And here we now have some actual data that demonstrates that, and that gives them a number to work with. Well, each 1,000 pounds you add, it's going to decrease your fuel economy by 5.344 miles per gallon, and thereabouts. Okay, so we always can interpret the slope in this way. This intercept can be sometimes interpreted, and I don't know if I've got a very good example here, but how do I get the intercept? And the answer is, if I put in 0 for x, what happens? 0 times b1 is, of course, 0, and when I add that 0 to b0, I get b0 all by itself. So the predicted value of the y when the x variable is 0 is what the intercept tells us. Okay, so when I take the miles per gallon example and I put in a 0 for weight, I get 37.285. So that 37.285, that intercept, means that a car with no weight would be predicted to have a fuel economy of 37.285 miles per gallon. that's kind of ridiculous because, of course, we don't. How are we going to reduce the car's weight completely to zero? That's pretty ridiculous. But let's take another example. If we have the speed of the roller coasters and we put in 0 for drop, that means that the roller coaster with no drop would be predicted to have a top speed of 38.5 miles per hour. And again, kind of ridiculous. So this is the caution, is that the intercept can be sometimes interpreted. Well, the slope always is interpretable, but the intercept can sometimes be interpreted if it makes sense that the x value can be 0. Having no drop, having no weight doesn't really make sense. And so in these cases, it's kind of sketchy to say, well, this 38.5 tells me how fast a roller coaster would go if it had no drop at all. Okay. One question might be, well, since you can't make sense of that intercept, why not get rid of it altogether? And the answer is, well, it actually doesn't function primarily as that thing where it crosses the x-axis. In fact, the intercept is just setting the level of the line up and down. The slope tells me how steep the line is, but the intercept moves the line vertically up and down. Changing the intercept would change the vertical alignment of that line. And in fact, the best line of best fit goes through this magic point, which we saw in the last unit, that is the mean of the x and the mean of the y. So this point, x bar, y bar, right? So that's the mean of the x and the mean of the y. That's that point which we used when we were computing the calculation. That's kind of the center point of everything. That point is always part of the line because of what the intercept is. The intercept is chosen to make it go through that particular line. And we kind of can see that because there's the x bar and the y bar in the formula for how I compute the intercept. So that's really, even though this intercept is not interpretable, it is necessary to have it in. Okay, so we need it, but obviously not for the interpretation necessarily.